All right, we're good to go. Um, cool. So, couple of things happening this afternoon. So, first part of the course, I want to go over a little bit of the administrative stuff. Um, Look at the Canvas shell, talk a little about the syllabus, um, about Zoom, and some information like that. And then we're going to jump into the actual material of the course. We're going to start off digging into some set theory, and that'll be our first unit for discussion. Um, so my name's Nick, Nick Macias. I go by Nick. Um, and I teach this course as well as the rest of the 200 level computer science sequence, so CSE 224, 222, and 223. I also teach 250 and 270 in spring and summer, and I also teach a section of 101 each quarter. So some of you may have had me in other courses, some of you may not. Um, Hopefully everybody who is taking this course with the intent of transferring to a university after this year is also taking 224.
The camera's not default on.
Sorry?
Sorry, I
Oh,
was unmuted.
okay, no problem.
My apologies.
No problem at all. So hopefully everybody who's in here is also taking 224. If you're not taking 224 right now, send me an email if you're unclear why I'm asking that. Most students are doing the 200 level CS sequence hoping to transfer next fall to a university, and so typically you want to take all 4 CS courses. 224 is only offered in fall, so if you're not in there, shoot me a note and we'll talk about it and make sure you're doing what you need to do. All right, so obviously we're meeting through Zoom, right? And I don't really have any particular rules to tell you about Zoom. It's pretty informal. Um, I will suggest keeping your microphone muted unless you're using it, right? Just to keep down background noise. But if you want to get my attention, if you want to answer a question or ask a question, don't hesitate to just use your microphone, right? That's the surest way to ask a question or make a comment. If you want, you can send me a message in chat also. I may not always see it. If you ask something in chat and I didn't respond, go ahead and turn on your microphone and just ask a question like that. I do record these lectures, so what you're seeing here, whether it's something that I'm writing on a piece of paper or a browser window where we're looking at a course syllabi or something, that's what will be recorded in the video, and that's what you'll see and hear. Whatever you're hearing right now, that's what will be in the video. I don't put the chat window up here. I don't put the list of participants up here. So if you're concerned about privacy, right, you can use something other than your actual name, so that others don't see, and so on and so forth. So if you have any concerns about the recordings or about how to present yourself in Zoom, let me know, or ask now. I don't require cameras. I encourage people to use their cameras, though. It's fairly mind-numbing to be on Zoom all day, right? And a lot of you will be in, CSE224 for an hour this morning, and then an hour and a half of 215, and you may have other classes also. That's a long time to just basically sit and stare at a laptop, right? If you put your cameras on and you can see other people and they can see you, it tends to make it feel a little more like a classroom experience. And this is really intended to be, an interactive lecture-based class. It's not an online setup. It's really, we're meeting at this regular time on these regular days, and we're talking about, discrete structures. Anything that makes it feel more like an in-person class would is going to help make that experience more tolerable. So feel free to open your cameras if you like. All right, let me take a quick look through Canvas. And these tags you see up here are timestamps. So when the video is posted, those topics will appear in a list with clickable timestamps, so you can move around the video more easily. So let me open up Canvas. And let's hop into 215. So, first thing, our class has regular meeting times, right? It's not an online class where you just sort of watch the videos at your leisure. You're expected to be here every Monday, Wednesday, Friday, 12:30 to 1:55. And I will be taking attendance, so attendance counts. I'll go through the syllabus and additional course policies in a few minutes. Let me go through the rest of this first. So we meet by Zoom. You've obviously got the Zoom info if you're here right now. Office hours right now are every morning from 8:30 to 9:30, and there's Zoom info on there. But if you look in the syllabus, it will point you to engrcs.com/schedule, and this will always show my current office hours. So today is Monday the 20th, and I had hours at 8:30 a.m. and that's the same all week. But if something happens, if I decide to change these, if I can't make a particular day, right, this page will always show you my current office hours, and you can always ask me about it. And I'll announce major changes in class also. There's a textbook for the course. It's a open access free PDF download. Okay, it's big. Don't print it out unless you really like, carrying around lots of paper. But download this as a PDF, keep it handy. I will assign some problems from this textbook. So I'll say, chapter 4, section 3, do these problems. So you definitely want a copy of this electronically somewhere. But there's stuff in here that we don't go over, and there's also material we cover that's not in this text. So it's a resource, but it's augmented by an additional text that does have more of the material that we don't see in that first textbook. So those are resources. All right, as I said, I record my lectures, I post them to YouTube. I don't monetize them, Google does. So they started showing commercials in videos back in November, and I apologize for that, but if you're watching these and you don't have YouTube Premium, right, you'll have to sit through commercials. On Windows, if I refresh the screen 4 times, it skips the commercials until the next commercial break. Some people have told me ad blockers and Opera will work really well together and so on. But anyway, so sorry that there's commercials in those. This is a link to the lectures, and there's a few lectures up already. So there's some kind of boilerplate stuff up here that are for mainly the other class. And I've had two 224 classes this morning, and so those lectures are posted. So after this afternoon, right, there'll be a CSE215 for 2021-09-20. So you can find the videos here, and they can be useful to go back and refer to. So you don't have to furiously take notes for everything that I say. Nonetheless, note-taking is a useful strategy for understanding and better learning the material. So I do recommend, some note-taking, but it's not strictly necessary. So those are available. There's also a subject index, which does not have anything on it right now, but this will get populated with a list of topics as we go through, and you already saw this in 224. Just like in 224, there's a Discord server for my classes. It's not required. It's very informal. It's not moderated by me. It's basically just a way that students, if they want, can connect with one another, socialize, ask questions, look for help, whatever you want to do with it. I don't require it. I don't do anything on there that won't also be discussed in class or on Canvas. So, but if you find it useful, if you like Discord anyway, it can be fun to hop on there. I have not taken attendance yet, so you're okay. But so I will be taking attendance. And since we're in Zoom, I can't pass around an attendance sheet. So here's how we're going to do attendance. I will tell you a few times during lecture that that I'm going to take attendance. And when I do that, what you want to do is send me a direct message with your Canvas name, a dash, and the word here. Okay, so let's go ahead and do an attendance ping right now. Go ahead and send me a message with your name, a dash, and the word here in uppercase. And you want to make sure you stick to that format. Okay, in particular, make sure this is your full name as it looks in Canvas. This is semi-automated, the recording of this. But I also save these logs. So if you were here on Tuesday and you didn't get credit for it, you can tell me that you were here and I'll go back and look at the logs and can correct it. Make sure that here is uppercase though. Because that's part of the scraping of it. I don't care about spaces. You can put them around the dash or not. That'll work either way. All right. So if you happen to be away when I take attendance, you want to be able to get credit for it. So if you're going away from your keyboard, I'll ask you send me your name, a dash, and just the word AFK away from keyboard. And then when you come back, just send me your name and a dash and the word back, B-A-C-K. And then, you know, if you go away for a few minutes to take care of something and I take attendance, then I can look in the log and I can see, oh, you were here, but you went away for a few minutes and then you came back. I took attendance in between. You'll get credit for it. All right, so that's all there is to that. Now let's see how we're doing. All right, so that looks pretty good. And looks like we're only missing a couple of people. All right, awesome. I think we're all set. So I'll do that a few times during the lecture, depending on how good my memory is. All right, so that's attendance, and you basically have 1 point per day for being here. So it's 3 points a week, unless there's a holiday. All right, let's see. So homework, there'll be roughly one homework per week. There's no homework this week, though. We'll start, the first assignment will be due on the 29th. Homework is generally due on Wednesday mornings at 8 o'clock. So we'll talk about homework more on Wednesday. Make a note of that. And I've got your first assignment posted, so it's some questions on set theory. And Wednesday we'll talk about this guide to writing up homework, but take a look at this first. Preview this on your own and see if it makes sense. It's a one-pager, basically how I would like you to write up your homework. So your homework for this course will be written out on paper, and your best bet is to write it on paper and then just take a picture of it and submit the picture. But you want to get good at, you know, making a picture that's got good contrast, is easy to read, is not fuzzy, and is not, you know, really big, like 70 megabytes or something like that. So spend some time playing around with your technology. Come by office hours if you want some help. We can look at different ways to do this, but this is part of your toolkit of being a computer scientist, is knowing how to do something like take a written document and turn it into a PDF so you can share it with others. So this guide will talk about how I would like that homework written up, and we'll go through that in detail on Wednesday, but you can take a look at it before then. Let's see. All right, there'll be a couple of programming assignments for the course. I haven't posted these yet, but these will be C programming questions. And most people in here are already taking 224 also, so you'll be very comfortable in working on the Linux machine to write C code. But we'll talk about this aspects of this as we get closer to the first assignment, which I've scheduled for November. There's a midterm on the 27th, and then a final exam whenever Clark schedules it. And we'll use whatever the Clark final exam schedule is for this class's finals. So usually that's going to be Monday at 12 o'clock during exam week, but we'll look at that when we get closer to it. All right, so let's dig into the syllabus and additional course policies. So this is CSE215, discrete structures. It's a companion course to CSE224, 222, 223. It really kind of builds out the foundational material on which computer science is based. Some of this stuff goes back to Aristotle, and some of it goes back to the 1800s with George Boole and Ada Lovelace and so on. And very little of it is particularly modern, right? A lot of this foundational work was done, was finished being done half a century ago. So, so the material is pretty solid, but really, really important. All right, so so you've got my email address, my name, you've got Zoom information. I talked about the textbook, it's free download. These are the course outcomes, so these are the subjects that we are stating that you are in command of if you've completed this course with a C or better. So in some form, we'll be going through all of this material. Possibly according to this tentative schedule, but this doesn't usually last very long. We are going to start off with set theory this week, and we'll probably go on to logic next week. But after that, sometimes things slip or extra things get put in and so on. So, but we'll cover all this material by the end of the 11 weeks. All right, grade for the course. So, homework, 20% of your grade. And you'll have a homework assignment each week, which will be due Wednesday morning, starting a week from this Wednesday, so the 29th. And I'll generally grade one problem from the assignment, but you don't know which problem I'm going to grade, so you want to work on all the problems and assume that every problem could be the problem that I grade for your entire grade on that homework, right? Which means if you are not sure how to do a problem, don't just skip it and say, he's only going to grade one problem, it probably won't be this. Come to office hours and ask, right? Let's make sure you know how to do all the problems on the homework. 2 programming assignments, total of 10% of your grade, so 5% each. And those are not, super difficult programming assignments in the sense that we're not using, fancy programming techniques. We're not getting into data structures and dynamic memory and stuff like that. The goal of these assignments is to take what we're learning in class and explore it through using some programming. So the thing you're trying to code might be complex, but we're not expecting you to use, very complex programming techniques. Most of this can be done with just some straightforward C code. Attendance, 10% of your grade, so we meet 3 times a week for roughly 10 weeks, so about 30 class meetings. So 0.3% for each class. 25% of your grade comes from the midterm, 35% from the final exam. All right, I will encourage you to read the remainder of this, since most people here were probably in 224. I've already talked about this. But make sure you read through the support services and college-wide policies. In here, additional information, emergency assistance is available, accommodations for religion or conscience. These relate to classes. If we're in person, we're not in person right now. We may be back in winter, but since we're on Zoom, you don't have to wear a mask. Yay. And then Code of Student Conduct and ECS policies. You can click through on those. And so those are sort of the general policies about the course itself. Here's a couple of pages about this particular offering in fall of 215. So the first thing to note is getting help, right? If something is unclear, if I'm talking about something and you're like, I have no idea what this person is talking about, or he keeps using the word null set, and I don't know what a null set is, right? Just ask a question in class, all right? It's a safe space to ask questions, and that can be really hard. Sometimes I never liked asking questions when I was a student. You know why? Well, one, because I was kind of shy. Two, because I figured I must already be expected to know this, so I must have missed something, and I don't want to let the person know that I wasn't paying attention, right? And three, I would rather, wait till class is done and then go back through my notes and my book and try to figure it out myself. All really bad policies, right? It's a whole lot better for you if you just, come into chat or use your microphone and say, what is a null set? And maybe I forgot to say what a null set was, Maybe I said it, but I said it in a way that was confusing. Maybe you just didn't notice when I said it, It's okay. We're here to learn. We've got an hour and a half, 3 days a week. We got plenty of time. And if you want a better chance of staying awake, right, being interactive is going to help with that. And if you're confused about something, probably other people are too. Especially like if I'm using a term that I forgot to describe, right? Probably the whole class is like, what the heck is a null set? What's a null set? And you're like going back, looking through your notes and so on. Just ask, You can send me a chat message, send a direct message if you're afraid, that other people will see it, and just say, I don't know what a null set is. And we'll go back and review that. So that's your best bet, right? If you can't ask during class, or if, a question comes up while you're working on homework or something like that, come to office hours. Okay? Every day, 8:30 to 9:30, I'm there. Come by, we can screen share, we can talk about what you're doing, we can look at what your solution is so far, and so on and so forth. Email, probably not a good way to try to get help, because email doesn't work well for back and forth, and if you have just a simple question like, what time is the homework due? Or are we supposed to do question 15 because it looks like we never went over the material, right? I can probably answer that in email. But an email like, I'm having trouble with proofs, right? Well, that's really something we need to have a back and forth dialogue about, right? So my response will probably be something like, come by office hours tomorrow. You're welcome to talk to other students, and in fact, I encourage students to talk to one another and work with one another to understand concepts. But be a little careful with that. If you're finding that you're fundamentally lost about something, come to me first. Okay? If it's something pretty small, you're stuck on one problem, you can't figure out how to do this proof, or the problem looks ambiguous or something, you may find some good help talking to other people. You can hop onto Discord or whatever. But if it's like, I really don't know how to do inductive proofs, right? Don't start looking at YouTube videos. Don't try to find a friend who's taken the course and get them to explain it to you, unless you also talk to me, right? Because a lot of the stuff we're doing, there's a lot of different ways to approach it. There's a lot of different ways to focus on certain aspects of it. There's certain aspects we're going to ignore. And you want to make sure that you're learning this in a way that harmonizes with what we're doing in class. And your best way to do that is going to be to talk to me. All right, Discord server I already mentioned. Attendance I already mentioned. There's a reminder for how to respond to attendance pings. Academic dishonesty, honesty, just do your own work, right? make sure that when you are working on the homework, you're doing the homework yourself. Don't go to online sites. Don't go to Chegger, Course Hero, or places like that. Um, it's way too easy to think you're doing your own work, but actually be turning in someone else's work. And if that happens, it's going to be a 0. If it happens again, it's an F for the course. Um, so so uh, so make sure you're doing your own work. And if you're stuck, if you don't know how to do a proof, if you don't know how to answer a question right, come to me for help. Um, you'll never get in trouble for doing that. All right, late work, which is mainly going to be programming assignments and homework assignments. You have a total of 4 slip days you can use if you're going to miss a deadline. If you don't use a slip day and you miss a deadline, you get a 0 for the assignment. If Canvas says it was turned in 2 minutes late, it's a 0. Okay. But if something's happening and something came up, you were going to do your homework this morning, but instead you had to, take the dog to the groomer or something, right? You can use a slip day. Send me an email and say, hey, I want to use 1 slip day for homework 4. I'll turn it in by tomorrow morning at 8, right? And you're good to go. But you got to send me an email and let me know you're going to use a slip day. And I would say save these for emergencies. So if something comes up that's beyond your control, you can use a slip date. Programming assignments, we'll talk more about those when we get closer to the first assignment. And other policies may be mentioned in class, right? So you're coming to every class. We're recording the lectures. There may be things that I say in here that are important. So as far as policies and procedures, so you're responsible for any changes that we mention in class. All right. Any questions on any of that stuff so far? That's basically the administrative side of the course. All right, cool, because most of what I've been doing today is talking about administration, so now we get to actually talk about like some computer science. All right, and I'll often take a break partway through class, so it's an hour and a half class. So if I remember, maybe like ballpark, like 1:15 or so, we'll take a short break just to kind of stretch our legs and brains. Let's see. So for the programming assignments, so someone said it's been a while since I've taken CSE121, but we'll basically be coming up to speed in 224. So by the time we get to the programming assignments in here, if you're in CSE224, you'll have done plenty of C and plenty of work on Linux, and so that will be more than enough review for the C you'll need to do these assignments.
I have a little question from that syllabus you just showed.
Sure.
It mentioned C and C++. Is there any reason why we couldn't use either or in probably both 224 and 215?
So I was a little surprised when I saw that on there because I used to allow C++ for 215 and I thought I had taken it off, but apparently I think I put it on there. So I'm okay with using C++ for 215, but definitely not for 224. 224 we're going to want to stick with very generic, basically Kernighan and Ritchie C. Because 224, our goal is really to sort of understand things from a foundational level up, and same with 222. So for those, it's going to have to be straight C. Does that make sense?
Okay. Yeah, I've just been doing a lot of straight C++ lately.
Okay, cool. Well, that'll make 223 all the more easy for you.
Yeah.
And if you can do C++, you can do C, right? So it's like a superset. All right. Um, all right. So what is this course? Discrete structures. What does that even mean? Discrete structure. I mean, we know what structures are, but I mean, bridges are structures, and discrete is like not telling someone a secret. So are we studying bridges that don't give away secrets? Probably not. Um, so what does the word discrete mean to you? Any sense for what discrete means other than, someone who's discrete with secrets? Um, what does it mean in a more mathematical or computer sciencey notion?
There's something in the background.
Yeah, go ahead. Someone just shout, and usually someone will win out.
Is it like the opposite of continuous?
Exactly.
Like what?
Yeah,
Finite.
that's perfect. There's kind of two ways of viewing things, whether it's mathematics or space time or whatever. There's discrete and continuous. And discrete structures is really the far endpoint from continuous structures or continuous things. Um, so what is continuity? What do we mean by saying something is continuous?
It's infinite.
It could be, or it could not be.
Is it that one thing seamlessly transitions to another state? Well,
Yeah.
it's like it broken up into very specific chunks.
Yeah. So sort of seamless transitions from one thing to another, or chunkified, which I think is a real computer science term.
Analog versus digital.
Or analog versus digital. Good. Awesome. So continuous, in a everyday manner of speaking means, you know, something that's happening without interruption, right? Continuous music performance would be one that never ends, right? It goes on and on forever. A little bit like infinite, right? Um, and that relates to things moving from one thing to another without a break in between, right? So this seamless transition, and that's also if we think of like CSE120 or where we look at circuits, right? You could have voltage coming out of some part of your circuit, and it might change from 0 volts to 5 volts, but it does that in some sort of continuous way. Where if we have time over here, right, as time increases, this voltage slowly rises up to 5 volt, and it might not go, in a straight line. It might follow some smooth curve and so on. Whereas in a discrete case, like where we had a digital system, maybe you've got an inverter that's outputting 0 volts, and then the input to the inverter gets connected to ground, and suddenly the output is 5 volts. And it's this jump here that makes this discrete or chunkified or digital. And in fact, if you blow this up, this isn't an electrical engineering course, but we're talking double E anyway. If you blow this up like on an oscilloscope and you look really closely at what's happening here, you would find that it's not actually a straight line. It's actually a really steep curve. And maybe it overshoots a little and then it smooths out. But it actually is continuous, right? And these digital circuits we use in Engineering 250, they're not actually digital. They're continuous. They're part of the universe, and the universe is mostly continuous. But we treat them as being digital. So that's the whole A to D conversion business of 250. We don't care about that anymore. But this idea of chunkified versus seamlessly transitioning, this is sort of the key of discrete. So what we're interested in this course is the study of things that we can break into these separate pieces, right? So for example, digital logic, where we could have either a logic 0 or a logic 1, And we don't think about logic 1/2 or 2/3, right? We have two logic levels, and we just go between those.
I did some research on what a discrete structure actually kind of was.
Oh, cool.
And one of the examples I always got was like, if a computer needs to draw a circle, it has to draw it, like, the circle has an infinite number of points around a point, right?
Mm-hmm.
But you have to quantify that in some way with an actual computer, right?
Mm-hmm. Right, right. Yeah, so if we wanted to draw a circle, we could make a program to draw the points of the circumference, but we can't draw an infinite number of points. We don't have enough time in our life to wait for a computer to draw an infinite number of points. So we would draw a point every degree, or every 100th of a degree, or something like that. And so this is part of why discretization and discrete structures come into play in computer science. When you look at your monitor, right, you're not looking at something continuous. You're looking at something discrete. You've got, 1980 by, 1020 pixels, and your image is 2 million individual dots. And those dots aren't any color that you want. They're one of, say, 24 million colors each. It's a lot of little tiny chunks, but it is still chunkified. And so much of our setup for computer science is based around this discretization. And it's a bit artificial because the universe is, tends to be more continuous than discrete. But we're not very good with doing computer science in a continuous way. So we approximate the continuous things around us by discretizing them. And that's a lot of what goes on in this course. So what are we going to study in particular? It's going to be a mix of things. So we're going to study a fair amount of math. But the good news is we're not going to do math like you do in Math 151 or 152, right? Because that stuff, that's all continuous, right? All that stuff you do with epsilon delta proofs and, limit as delta t approaches 0 and all of that, that's continuity. That's trying to use the mathematics that was developed by our sort of, discrete understanding of the world to get our hands on continuity, to understand what happens as these chunks, these spaces between things get smaller and smaller. We're not going to worry about that. We're doing discrete math in this course, but there is some dose of math that we'll be doing. We're also doing a lot of logic. So logical reasoning, propositional calculus it's called sometimes. If A, then B, right? This is a way that we can understand why computers do what they do. And that we can ask, here's a program, will this do this thing that I want it to do? And how do I know it's going to do that? And will it do it tomorrow? And if somebody puts in some number that's never been put in before, will it still continue to work? So we're going to look at logic, and in particular, we're going to look a lot at proofs. And there's obviously a good dose of computer science in this course. It's a CSE course after all. But we'll look at how this stuff relates to computer science, as well as looking at some of the foundational aspects of things like Boolean algebra and state machines and things like that. There's also a healthy dose of weird stuff. And the weird stuff is why discrete structures is one of my favorite topics. And a lot of what we do in this course is going to follow the same general roadmap, which is we're going to begin with something that we probably already have some understanding of. So today we're going to start talking about set theory. And most of us have encountered set theory in school, and we have a pretty good idea what set theory is. We know what a set is. We know what happens when you combine two sets. We know how to count how many things are in a set and so on. So like most topics in this course, we'll start with something that we're already familiar with and that we have some understanding of. and we'll begin developing that subject very rigorously. And what we're going to find is that if we get rigorous enough and we develop a subject far enough, we're going to find ourselves somewhere different from where we thought. And we're going to start seeing weird stuff. And this is exciting because it keeps the course interesting, and a lot of students have told me this is their favorite computer science course of the sequence. This subject is their favorite. But it's also a little treacherous because if I start lecturing on set theory and I start telling you, you know, what a set is, it's really easy to tune out and say, oh, I learned this in 7th grade, you know. And you check back in 20 minutes later and we're writing weird symbols on the paper and talking about concepts you've never heard of, and you're lost, right? So if we're starting with something and it feels, you know, sort of fundamental, like something that you've already encountered before and you understand well, stick with me. Right? Go along for the ride. If you get through this course and you haven't learned a single thing, right? That's what you call a good problem to have, right? If it turns out you knew everything that we're going through in this course, but that's probably not going to happen. There's probably going to be directions that we take these subjects that will surprise and startle you, and should be a lot of fun. All right, so let's do an attendance ping. So send me your Canvas name and the word here in uppercase, and as soon as you've done that, we'll take like a 5-minute break. We'll come back. We'll start talking about set theory. So do a quick break, and we will come back at 4.5 minutes from now. All right, so I'll be back. All right, that mic is still recording. It's not broadcasting. Alrighty, welcome back. Well, let's start talking about set theory then. So what is a set?
It would be like a collection, right?
It's a collection of things. So here's a set of pens, right? It's just a collection. Here's a set of remote controls. Here's a set of things. It can be a collection of almost, anything that we choose. Well, we usually have some idea what the universe is of things from which we can choose. So a set of pens, would not contain a remote control, for example. But, it might contain a Sharpie, and it might contain a fountain pen, and it might contain a ballpoint pen. And this is not a bad definition. We can define a set as a collection of things. And that'll work for a few days. But we have to be a little careful about this notion of things. Things is not a very precise sounding word. And maybe we really mean just a collection of things. Maybe we don't care what sorts of things you put in there. Can we put a mouse in our set? Sure, why not, right? But it turns out, if we're not totally, if we're completely carefree about what sorts of things we can put in a set, we can get into trouble. And so around the beginning of the 1900s, when people thought of sets as collection of things, people started to discover what are called paradoxes. Questions that had no possible answer because they revealed a fundamental contradiction in the nature of things. And in set theory, if we just think of a set as being a collection of things, we can quickly get to paradoxes. And we'll play around with one probably on Friday called Russell's Paradox. And it was really a breaking point where people went from this sort of kind of hand-wavy or naive notion of set theory to what's called axiomatic set theory, which is very rigorous and strict. But we're not going to worry too much about that. We'll be okay with just, a collection of things. But we'll look at some of the problems we can get into with that probably at the end of the week. So for now, we'll think of it as a collection of things. But let me write that in a way that sounds a little more precise. And I'm going to add a word. I'm going to say an unordered collection. And I'm going to say of objects. Or these could be elements, or members, or I suppose things. But I want to add this new word. Sorry, go ahead.
You might have, or just about, this might be skipping ahead a little bit, but I've watched a video about how to count past infinity, and
Cool.
it describes sets that are well ordered. What would the distinction be between unordered and well ordered? Working to talk about it.
So yeah, that does get a little far field, but unordered, I simply mean there's no such thing as, what's the first element in this collection of pens. I've got 3 pens, I can count that, but which pen is first? Well, if I look from left to right, this one is first. But, if I do them like this, which one is first? Well, maybe I'll go from top to bottom. I can put an ordering on the elements of the set, but by itself, the set has no inherent ordering. A well-ordered set is a very particular type of ordering that can be placed on a set. And the set itself is still, inherently just an unordered collection of objects. But there are different orderings we can put on there. For example, I could order these by height. Right, and they might go like this. So a well ordering is just a particular way to assign an ordering. and you're on the cusp of some very deep and very weird mathematics as soon as you start looking at well-ordered sets. And if you haven't already bumped into Zorn's lemma or the axiom of choice, it'll be exciting when you get there. And those are all tied into counting beyond infinity. We will get into infinite sets later this week and looking at degrees of infinity. So we'll get into some of that stuff also. So yeah, you're reading some good stuff. All right, so we'll think of a set as an unordered collection of objects. And we usually represent these with just, an uppercase letter will do. So we could say, S is a set. And if there is an element of that set called X, we can say X is an element of S. But if we're doing math, we like to use funny symbols and not write too much. So we use an epsilon to say X is a member of S. So that's the membership symbol. And if X was not a member of S, we could write an epsilon with just a little slash through it to say X is not a member of S. So those are shorthands that we'll use quite a bit. All right, well, I gave you some examples with pens and remote controls and mice. But usually our examples will be more mathematical in nature. So, for example, there's a standard symbol. It's a Z with an extra line going down the diagonal. So I call it a funky Z. This is the set of all integers. So what's an integer? It's a positive whole number, a negative whole number, or 0. So I can't write down all the elements of this set because there's an infinite number of whole numbers. But I could use a notation, an informal notation, to show you what the elements of the set are. For example, I could say it contains 0, 1, 2, 3, ... And also -1, -2, -3, and I can put a ... before. Now this is a little potentially ambiguous, right? If it's really clear to whoever's going to look at this that by this I mean all the positive integers, negative integers, and 0, then this is a good notation. But, this would probably not be a good way to represent the set of all integers. Because I don't know exactly what goes in these dots after this, right? Maybe it's only integers that are the square of something. So it's 0, 1, 4, 9, 16, -1, -4, -9, and so on, right? So you'll see this notation. But when you use this, you want to make sure it's pretty clear to the person who's going to be looking at it what you mean by this. And so if you mean the set of all integers, we just use this funny symbol Z. And that sort of universally says the set of all integers, positive, negative, and 0.
Could you show the notation for, like, X is not a member of S really quick again?
Yeah, so I could say, 1.5 is not a member of the set of integers.
Oh, across for the epsilon.
Yeah.
I thought you just meant a dash. Oops.
Oh, okay. But, 3 is a member of the integers. I could say P equals the set of all prime numbers. We'll talk about primes a fair amount in another week or so. But primes are positive integers bigger than 1 that are not divisible by any other number except themselves and 1. So for example, the numbers 2, 3, 5, 7, 11, 13, and so on. So this is not a standard symbol, but I'm just saying, you know, for example, P could be the set of all prime numbers. And so it would contain these. Which, by the way, would be the same thing as, you know, I could list them like that. Because it's unordered, right? So when you have a set, really it's just this collection of objects. And for any object in the universe, you can ask the following question. Does that object belong to the set? Is it a member or not a member? Right? And the only thing that a set is it's a set of answers to that question. Is such and such a member of the set? So is this mouse a member of the set of prime numbers? No. Is the number 31 a member of the set of prime numbers? It turns out, yes, it is. And we can go on all day creating sets of things. So what do you think the set E is, if you were to describe it in words?
All even integers.
Yeah, that's all even integers. There's other ways we could write this that might be more clear, but, you know, pretty good assumption that somebody's going to look at this and say, yeah, it's a set of even integers. So that's a valid set. We could define the set of odd integers, and so on and so forth. All right, we got a link to a YouTube video in chat, which talks about some of these topics. Cool, I'll check that out. And another one. So I don't know if anybody here, well, I'm sure some people, I don't know if, and maybe that's one of those links, but there's a YouTube channel called Numberphile. Really interesting channel, and there's a lot of crossover to some of the stuff that we'll be doing this quarter. Just all kinds of interesting videos related to numbers and discrete structures and such. So a different way we could describe the set of evens is using the following notation. So let me write this in words first. E is the set of all integers x such that x is divisible by 2.
Would it be incorrect to say E is the set of all even integers? Would that be too shorthand?
That would be a perfectly accurate description of this. So let's write that one first. E equals the set of all even integers. And that's the absolutely unambiguous way to describe what E is. But if you wanted to describe it a different way, if someone's like, I'll give you $20 if you can describe this without using the word even, you could say x is the set of all integers x such that x is divisible by 2, because that's what it means to be an even integer. It means you're divisible by 2.
Would you say including 0 too? Because I'm not sure if it's an even or odd technically. But
So 0 is technically even,
okay.
right? So it does belong here. And what do we mean by divisible by 2? I mean, I have a calculator. I can divide anything by 2. Right? I can put in pi and divide it by 2. But we're kind of assuming when we say x is divisible by 2, we mean, you know, divisible by 2 without anything left over. So 10 is divisible by 2, but 9 is not, because if you take 9 and divide by 2, you get 4 plus an extra 1/2. So, but we'll talk a lot about divisibility later also. But if we just think of it as like, you know, evenly divisible by 2,
So 0 would still fall into that, because obviously 0 divided by 2 would be 0.
yeah, 0 divided by 2 is 0, which is a whole number. So 0 is technically divisible by 2.
Is this a universal variable, or is this like the P one that we made up?
This is just an arbitrary letter I used.
Okay.
So yeah, so far we've only got one sort of universal symbol, which is the funny Z. But we'll see a few more in a minute. So if I wanted to write this in a more succinct mathematical way, I can use the following notation. So I could say the set of all x contained in the set of integers, and then I can write a colon, and this colon is short for such that x is divisible by 2. And sometimes you'll see a bar instead of a colon. I'll use a colon, but sometimes books use bars. So this is a precise notation. The set of, that's what the curly brackets mean, all x contained in the set of integers. So this is the set of all integers such that that integer x is divisible by 2. So this is a more succinct, precise way of writing this sentence up here. And so I could write the set of all odds, let's say D, is the set of all integers such that x is not divisible by 2. Well, there's a description of the odd integers. All right, there are some sets that we'll pay attention to which are called singleton sets. And a singleton set is a set that contains only one element. So for example, that's a singleton set. It contains a single element, the number 5. If I had a set containing just this red Sharpie, that would be a singleton set. It contains one element. And that's pretty close to another concept, which is the empty set. And the empty set contains 0 elements. So like that. So this is a singleton. This is called an empty set. Contains no elements. So what's an example of an empty set? I don't know. The set of...
Same as the null set.
That's the same as the null set. So the set of all x such that x is bigger than 10 and x is less than 0. Well, there's no possible... I'll do the set of all x and z. There's no integer that's bigger than 10 and also negative. Can't be. There's nothing wrong with writing this. It's a perfectly fine thing to write, but it's equal to a set containing no elements. Right? If I tried to show you the set of pencils that I have on my desk, it would be an empty set because I don't have any pencils on my desk right now. And we have a special symbol for this, which is a 0 with a slash through it. So that's a shorthand for the empty set. And it's because brackets get annoying sometimes if you have too many of them. So we just have a special symbol. It doesn't require us to draw brackets.
I have a quick question. Will the empty set be important for like proofs? The idea that since blank is not the blank of the resulting set is like empty, something like that.
Yeah, it can pop up in proofs. Like if you want to prove that something is false, you could go about the process of trying to make a set of all the conditions under which this is true. And if you can prove that set is empty, then you've proven there's no cases or conditions under which it's true, and therefore this thing is false. It's actually a really powerful concept, which is funny because it's nothing, you know, but it's a pretty powerful nothing. All right, so examples of sets. We already talked about this, which is a set of all integers. We sometimes talk about a funny looking n, which is the natural numbers. And what is a natural number? Most often,
It's no negatives, right?
it's no negatives. So it's the set of all integers that are bigger than or equal to 0. But some textbooks, some papers don't include 0 in the naturals. So there's a potential ambiguity there.
Yeah, it just feels like one of those, litigious wars of mathematicians.
Yeah, totally. So I usually avoid natural numbers, but it pops up in the book sometimes. So if you encounter it somewhere, right, just go back and look at the definition, see what it's defined as in whatever context you're looking at. But let's talk about this term, natural number, right? What's unnatural about -3?
You can't have -3 things.
Yeah, you can't have -3 pens. I can have 1 pen. I can have 2 pens. I can take away a pen and come back to 1 pen. But can I take a negative pen and put it here and have it somehow obliterate this pen? It's not how nature seems to work. So all this stuff, the mathematics that you're tortured with in school was not simply created by people who were bored and wanted to come up with confusing concepts. Most of the mathematics that's been developed has been done in an attempt to understand and make sense of and equip us with the machinery to make statements about the natural world, right? About the universe, including the universe inside our minds, which is where things get kind of funky. So, when people started counting, they said, I have 1 rock, I have 2 rocks, I have 3 rocks. And people were counting before they were doing addition. And, someone may have noticed that they have 2 rocks and they get 2 more rocks. Now they have more rocks. They actually have 4 rocks, And if they have 2 horses and they get another 2 horses, now they have 4 horses, right? But to go from those experience to understanding what this means, that's a huge leap. This is called abstraction. This is the idea that 2 of anything plus 2 of the same thing give you 4 of that thing. And that's not obvious, right? We learn it early in school, so we take it for granted. But the leap to, 2 rocks plus 2 rocks equals 4 rocks, 2 horses plus 2 horses equals 4 horses, 2 pens plus 2 pens equals 4 pens, to be able to generalize from that and just come up with this idea of, 2 plus 2 is 4. Well, 2 what? 4 what? Just 2, right? Taking this as an abstract concept, that was a huge leap in human development. And so, we introduced the idea of numbers, integers. And 2 is fundamentally different from 2 pens or 2 rocks. It's an abstract notion. But when people started doing this, the numbers that they were working with were always numbers that could correspond to, how many rocks or how many cows you have. And so the idea of a negative number didn't correspond to nature. It wasn't natural. And even the idea of 0 didn't seem to correspond, because having 0 rocks is kind of a weird thing, I've got 0 purple dragons on my desk right now. It may be a true statement, but it's a little bit bizarre, right? So 0 itself was a little bit of a diversion from the way we use numbers to count. And negative numbers, whole nother world. You got to be a real weirdo to talk about negative rocks, you know. So we call these things natural numbers, and these negatives are, I guess, unnatural numbers. But it's simply how we develop them. So another symbol is R. These are the real numbers. Well, what's a real number? Tell me that's not a marketing term, right? So a real number is, 2.714 or pi, or so on. We think of them as just decimal numbers, right? They're things bigger than the integers. It's basically any number that you can think of is a real number. And within the real numbers, we talk about rational numbers.
So this includes non-terminating, non-repeating decimals, right?
Correct, yeah. Like pi, for example, it never ends, but there's no pattern that repeats forever, like with, 3.333. But that's still a real number.
3.333 is also a real number?
Yeah, it is.
Okay.
So 10/3. That's a real number. Pi is a real number. And, 2 is also a real number. And 0 is a real number. And -5 is also a real number. So real numbers are pretty much any number you can think of. And then there's rational numbers. So does anybody remember what rational numbers are?
Those are just fractions, ain't they?
They're just fractions.
I have a question. Do real numbers also include negatives?
They include negatives, yep. So reals are pretty much any number you can think of. And that's the funny R. So rationals, which is the funny Q, those are fractions. So those are things like 1/2, or 0.5. Or 1/3, which is, a repeating number that goes on forever. Those are all rational numbers. What about a number like 7? Is that rational?
No, it's not a fraction, right?
How about that?
This is just 7/1. That's
Yeah.
right.
So that's technically a fraction, so that's still a rational number. And -5 is also a fraction. And these fractions don't have to be unique, right? This could be -15/3. But as long as you can write it as one fraction at least, it's a rational number.
So what's a rational number that's not a real number?
If you're rational, you're definitely real.
Okay.
So what about 0?
That could be a fraction like 0/5.
Perfect. So that's a rational number too. So we can actually say if there's some number x that's a rational number, then x is also a real number. So anything that's a fraction is also real. What about the other direction? Are there any real numbers that are not fractions? Pi. So pi is not a member of the rationals, even though pi is a member of the reals. And same with e. E is like one of the best numbers out there, if you had to rank them.
E is just approximately like 2 point something, right?
Yeah.
Yeah.
Yeah, it's the...
You meant to cross that epsilon, right? With the e's and the rationals?
Correct, thank you. That would have wrecked like all the mathematics.
Is there any real number that's not irrational? I'm curious about that question.
Any real that is not irrational?
Did I have it backwards?
So definitely any rational is going to be real, but there are real numbers like pi that are not rational.
Oh, okay.
So this is in some sense a bigger set than that.
Because a real by definition is just any number that's not imaginary, right?
Right.
So like, I don't know, the square root of 7, that would give you an irrational number, I guess, right?
Yeah, so square root of 7 is not a rational number, but it is a real number.
Gotcha.
And this is interesting. So this is called irrational. All of these terms, if you think about what they mean outside of mathematics, it paints an interesting picture of the mindset of, you know, whoever was naming these things. So why is a square root of 7 not rational? It's kind of ill-behaved in some way. You can't write it as a fraction, right? And I'll tell you the most irrational thing about these numbers. So you know the Pythagorean theorem, right? So a squared plus b squared equals c squared, unless you're a scarecrow, and then it's a little different. So Pythagorean theorem. So Pythagoras, he was a Greek mathematician and philosopher. He basically ran a cult. Okay, there was a cult of people led by Pythagoras who worshipped numbers. And they believed that numbers were a pathway to knowledge and a pathway to the gods and to, you know, universal understanding of the world. And they looked at numbers as sacred, so they developed all these ideas about numerology and which numbers were good luck and which ones were evil and things like that, right? So it was this whole cult. And they believed that, you know, if you understood numbers deeply enough, you would have great knowledge about the world. So they studied numbers and, you know, came up with things like, you know, Pythagorean theorem. But here's a really, really basic question. Suppose you take a square, the most basic shape other than maybe a circle, and you have a length and a width of 1 unit. So it's a square. Both sides have a length of 1. And you draw a diagonal. What is the length of that diagonal? And they were interested in this question, right? What number represents this length? Well, they knew it wasn't an integer. They knew it was bigger than 1 and it was smaller than 2. And it was approximately 14/10 or 7/5. And it's even closer to 141 100ths, but not exact. And so they were intrigued with this, right? Most basic shape, simplest dimensions, just 1 unit on a side. How long is this diagonal? And they were looking for what this fraction was that gave you this length. And somewhere along the way they made what was a horrifying discovery, which was that there was no fraction that represented this length exactly. You could get close, but it was impossible to write a fraction that exactly equaled this length. And that was a bummer. Because remember, these people thought that numbers were sacred. They thought that if they understood numbers, and to them numbers were, you know, integers or ratios of integers, they thought that if you understood these deeply enough, you would understand the entire universe. And all of a sudden they discovered that there was no ratio of integers that gave you this length. And that kind of like was a little rain on their parade. So they didn't tell anybody about this. This was like forbidden knowledge. And in fact, there was one member of their organization, he was a man in his 90s, I believe, and he started telling people about this outside of their circle. He disclosed that there was a proof of this fact. And some of the other people took him out on a boat to the middle of a lake and pushed him off to try to silence him. He actually made it back to land. But I mean, this really freaked them out, right? And so today we call this length, you know, the square root of 2. We have a symbol for it. Why do we have a symbol? Because we can't write a ratio of integers. And we can write it out, you know, as a decimal, but we can't write all the digits. So we just came up with a new symbol. So yeah, quantum mechanics would really annoy them. So this is an example of a number that is real, but is not rational. And so it's called an irrational number. All right, and somebody else used the word complex numbers. So this is a continuation of this, right? We know about square roots. We know the square root of 9 is 3. We know the square root of 25 is 5. This means 3 squared is 9, 5 squared is 25. The square root of 1 is 1 because 1 squared is equal to 1. But what's the square root of negative 1? And there's no real number that you can multiply by itself to get negative 1. Doesn't exist. Why? Because if you take any number and multiply by itself, the result is never negative. It's either 0 or it's positive. So how do we deal with this? We just invent a new type of number called an imaginary number or a complex number. And so we say I is just this symbol that represents the square root of minus 1. And so if we take the real numbers, things we can write out, you know, as decimals that maybe go on forever, and we also toss in these imaginary numbers, multiples of this and this added to other things and so on, we get an even bigger set called C. And this is the complex numbers. So we've got a whole compendium of examples of sets to work with. Integers, naturals, reals, rationals, and complex numbers. And in some sense that can be made very precise. We don't really need to get too much bigger than the complexes. We're not going to run into this kind of situation where we do something to complex numbers and the result's not complex. That's a whole nother topic that ties into a 21-year-old who died in a duel and was about 70 years ahead of mathematics. But so those are examples of sets. All right, so what we want to do next time, go ahead and send me one final attendance ping. Let me know that you're here. And what we're going to do Wednesday is we will start looking at...
Audio went out.
Did it? I
No,
think
I
I...
hear ya.
Okay.
I think that was just my internet then.
Okay, no problem. So Wednesday, what we want to do mainly is start looking at ways that we can take sets and compare them to one another and combine them to come up with new sets. So we'll start looking at set operations. We'll see some other ways to describe sets and to analyze them, and we'll start building up our ability to do set theory from there. All right, so send me your attendance ping. Once you're done with that, you're good to go. I will see you next time. Have a good afternoon.
I have a bit of a question not related to. What ink do you use for a fountain pen?
Oh, all kinds of inks. Jay Hebron makes some nice ones, and I do some Schaefer, and I just kind of like scout around and largely go to Amazon, unfortunately, and just try different kinds. And it's personal. Some people like different brands more than others. Noodlers makes really nice inks.
Yeah, that's the one that I personally use. I like Noodlers because I kind of like the archival quality of it.
Yeah.
And also the fact that if by chance I drop like water on it, it's not completely ruined.
Right.
It definitely ruins the page, but I can still kind of read it.
Mm-hmm.
But I just kind of want to expect that. I've tried out like a couple things. Because I'm lefty, I've kind of stopped using fountain pens because
Yeah.
how fast I need to write kind of conflicts with just the qualities of fountain pen.
Yeah, that's a bummer.
Yeah, but I found some weird workaround where like some rollerball cartridges, I was able to tear it apart, fill it with like fountain pen ink.
Oh,
put it
cool.
Together, and it kind of works in a weird way. It was I kind of have to let it dry itself out a bit because it comes out way too wet.
Okay.
With this weird solution, but it's like a weird workaround where I don't have to use. It dries faster than using fountain pen, but it's a weird workaround so that way I can still use all the ink I bought when I was really
Right, right.
but and still use it for school.
That's cool. Awesome. Nice workaround.
Yeah. I'm just curious. Any like qualities you kind of look for in your ink?
Oh, it's just all kind of like in the moment. I don't really have a whole lot of particular, where I would say, oh yeah, I love this kind of ink. Other than J. Hebron, I love their colors. They have such unusual colors. They're just like slightly different tones and stuff. Plus, their stuff is all, I think, vegetable based. So that's always nice. But doesn't always flow as nicely as some of the other ones. Noodler flows really nicely.
Yeah. I tried out like a handful of different things. I think it was I forgot what website I used, but you can get like a sampler pack.
Oh, cool.
When I would for a little while I was just trying out different ones, and I still kind of kept mostly the noodlers because I just really like archival quality.
Yeah, definitely.
But I know that I don't that like one of my favorite ones it was like noodlers legal blue.
Okay.
It has the archival quality, the bulletproof, whatever. But also, depending on what paper you're on, the blue can have a bit of a red sheen to it.
Oh, nice.
It's hard to achieve on most papers. I just buy the cheapest paper I can get because I write so many notes.
Mm-hmm.
But it's I would recommend if you ever like I've used up this ink, come get some of those. Looking into the Noodler's legal blue.
Cool. I'll try that one next.
All right.
Awesome.
Bye bye.
All right. Have a good one.